company was founded by Alain Roux 40 years ago, and in those days speakers were made a bit like musical instruments, where you sort of listen to them and say, oh, this sounds better than this one. But Alain's idea is that a speaker should just do one job, and that's to transform the electric signal into an acoustic signal accurately, and that you could measure this. So the products he manufactured and designed and developed evolved hand in hand with the measurement instruments, and started making speakers like this, passive speakers, all of them, two-way, three-way ones. And there wasn't much difference in those days between hi-fi speakers and studio monitors and things like that, so it was all about the same. Then we also started making PA, so where the aim is to have powerful and lots of pressure. So made those for a long time also, all passive again, but big horns and really big boxes that are still used around. But then about 25 years ago, a few things happened. First of all, we started manufacturing for Rowan, that's a hi-fi brand in Switzerland, and then we were also asked to develop a range of active speakers by Studer. So these were sort of small PA speakers that we had, and then we developed this range of speakers for Studer, which we manufactured for a long time for them until they were acquired by another big group that had their own monitors. So
you manufactured both the drivers and the amplifiers?
Amplifiers, boxes, some of the drivers we made here, yeah.
So the only thing they put on was Studer?
Yes, they were our development. And then when they stopped buying speakers off us, we were then allowed to relaunch our old brand. PSI Audio is what we sell now. About 10 employees, 7 full-time equivalent, and what's interesting is there's at least 25 different jobs that you have to do, so it makes our life very interesting, as we have to change job all the time. So this is a metal and wood workshop where we make bits and pieces like this that are very easy to make, but we make them here. Each time we ask for quotes outside, it's more expensive than doing them here. And what's very important for us is that we keep the entire know-how in-house. And then there are elements like this, the flask of the tweeter, that we have to machine one by one to 1/100th of a millimeter accuracy. So this has to be done here. So this is basically the cross section of the speaker, where you come in with an electric signal and you come out with acoustic signal, okay? So what we have is we have 2 drivers here. You can have 3, but this is a two-way system. So you need you need a high pass to send the high frequencies up here, low pass to send the low frequencies up here, yeah? So this is what you call the kind of crossover. Then you have the amplifier. So you have an amplifier adapted to, each time it's perfectly adapted to the membrane it's going to drive. Okay, so that's very important. That's one of the great advantages of having an active speaker. Then this driver doesn't move at the same speed at all frequencies. It has resonance frequency because it's a mass on a spring. So it has its resonance frequency of the mobile mass. The material itself has a resonance frequency. The suspension, the spider, and all of these means that you have to push it with different strengths at different frequencies. So this is why we have this feedback loop, which measures the speed of the coil inside the magnet and gives the information that is then EQ'd, or it goes through an EQ system, back into the amplifier and modifies the impedance of the source. So this is what we call our adaptive output impedance system, and it's basically a damping system, electronic, that depends on the physical characteristics exactly of all of these. At different frequencies, it's different. It has to be different. You can't just have the same damping system for all the frequencies in a system like this. And then, of course, any signal that goes through any type of filter, whatever it is, it could be acoustic, electronic, or mechanical. So the driver's a mechanical filter also. Any signal that goes through filters will affect the phase. So it'll slow down the lower frequencies compared to the higher frequencies. So what you want is to hear all these frequencies exactly in the same time. So the typical example is a snare drum that goes ta, Okay, and you want to hear the t and the high frequencies of the t and the low frequency of the a at the same time. And when it goes through here, the tendency is when it comes out, it'll give you a signal that sounds more like t a instead of ta. So you have to put them all back again in line. And this is what we do here with our compensated phase response. So all of this you could do with digital or analog technology. Digital is great if you want to memorize information, of course. Instead of having tapes or I don't know what, you can put it on a chip. It's very easy. So if you want to memorize information or you want to process information or process data, it's very useful to having digital technology. But we go in here and come out here. There's no memory. There's no processing, so you might as well fix it in analog technology and just do it in analog technology, and it won't change for the 30 years or 50 years time.
That's what you really do. That's also maybe your tagline, that you do it all analog.
Analog, right? Yeah. You know, okay, the source is often digital. I understand that because it's so flexible, but somewhere in the line you have to convert into analog technology, and especially in studios, people spend a lot of money and they spend a lot of effort trying to choose their conversion from digital to analog. They don't want another double conversion inside the speaker. There's no need for that. Adding latency, chopping up the signal, adding another conversion. You might as well keep it all in analog technology. The only problem with, the difficulties with analog technology is you have to do all this with little components. And these components, so you have to have a smart layout and smart architecture so that you minimize the amount of components, and then you need a very tight control of all the components that go on here so that it does its job exactly with as minimum error. So that's basically our speciality. We use a lot of digital technology when we want to develop filters and stuff, but once they're developed, because of the flexibility, you can change filters like this. But then once you fixed it, you fix it in analog technology and do it, and you have no latency, no chopping up of the signal, and it's seamless. And then the main thing that we do here is we do the coils that we use to make the tweeters. So basically here we have a very fine coil around here that's attached to this membrane, and then this coil has to go into a magnet. So this is a neodymium magnet, and it has to come in here. And what we need, if you want high SPL is pressure, so you want high pressure. To have high pressure you need high acceleration. To have high acceleration it's mass times force, so you need low mass but a strong force inside. So the magnetic force has to be as strong as possible. That means the gap has to be as thin as possible. That means all the mechanical adjustment has to be extremely accurate so that you can go back and forth 20,000 times or more per second without changing shape, size, or scratching anything. So here we're transforming an electric signal into vibrations, and we've done the opposite, transform vibrations into electric signal, whereas we made seismographs that have measure vibrations on bridges. So many bridges in Europe use the same technology for seismographs. Because in domestic electronics, what breaks first is always the connections.
The connections, yes.
So this comes from the automobile industry, the way of clamping them and all these connections. So it can vibrate for decades and decades without breaking. And in 40 years, we've never had a connection that's broken. First of all, you have a continuous supervision of everything you do, so you can see what you're doing and you can do it. And you can also adjust very easily the size of the solder to the components that are on the other sides. And you're very flexible if you have to change one or so this is why we do it this way for the time being.
The PCBs you also make yourself?
Those they are design, but we buy them, yeah. And then these are checked, so they're checked and pre-calibrated before mounting them on the back panel that I'll show you in a minute. We put them on the back panel. So here you have the heat sink that we saw before. We have all the power supply. So all this is made here. So we saw the small drivers that we make ourselves. The other drivers are our design also, but we have them manufactured. We outsource that. People think that this is what this makes the sound, but it's not this that makes the sound. It's the way you move it. It's the movement that makes the sound. And what's important is that the movement is perfectly adapted so that you know the physical characteristics of all of this. So it has to be well dimensioned. The engine, the strength, the how far it can move, and that you know the elasticity and the springiness of all of this, and then you have to adapt the electronics. But whether it's paper, plastic, or whatever exotic material, it has to move in perfect compliance with its physical characteristics. And what's important for us is that it's very regular in production, because otherwise you have to correct them all the time. And we check every single one of them when they come in, and we have between 10 and 30% that are outside of our specs.
Yeah.
So that's wood, compressed wood chippings, and it's the best material one of the best materials at least for acoustics, because it's heavy enough, it absorbs vibrations, it's homogeneous in all directions, quite easy to source, easy to machine and paint. So all high-end speakers are made out of MDF, most of them I would say, and if they want a perceived value that's a bit higher, they put exotic woods on it. But inside it's normally always MDF.
Yeah.
To be better than MDF, you'd have to go into things like ceramic and cement or things like that, which are much more complicated. HDF, it's not quite it doesn't last as long, it's more fragile and breaks also.
Okay. Yeah.
And it's also got a density where it rings a bit more. The only problem with wood, is that you have to physically catar and stick them together. You can't cast them or mold them. So this is why people that manufacture big quantities of speakers, they'll go on to something that you can cast, like plastic or aluminium. So these are made, yes, but these are made also just next door. We used to make our own, but then the logistics with the carpentry shop that we had was a bit too complicated, and we found a good partnership with somebody here. So when we say Swiss made, we mean 95% within a radius of 500 meters. So here's the assembly. So all this is done. Oh, you can see it by hand. This is the tweeter mid assembly that you can put on.
The tweeter you showed us.
Yeah, that's the one we showed you there. Yeah. Daniel Weiss uses these.
What? These
speakers. Daniel Weiss,
Yeah.
Claude Sellier. So that's just to check that they've been mounted correctly, and we do a pre-calibration in there. So that makes sure the electronics is perfectly calibrated. And then you put them in the box with the drivers, and you have to calibrate those together. So, and then each speaker, when it's finished and assembled, you want to check, as I said, the goal of a speaker is to transform electric signal into acoustic signal. So you have to check. So you send in an electric signal, and you measure the acoustic signal that comes out, and you want to measure what comes out of the speaker and not what comes back from the room. So either you go outside, or you need a room where there's no echo, anechoic room. Okay, and you can see.
You have that.
Wow, you can see a bit more of our new product in here. We're showing it next month, and they're prototypes only. It's not only product development we use this room for, but also production control. So when we develop a speaker, we try and keep it as flat as possible, of course, and the idea is to have the widest bandwidth and the highest SPL and the flattest response. So we do that, and then you have to test it. So you have to listen to it, of course, because there's lots of little fluctuations and there's different things you can do. But you have to test it in different rooms with different people. So we have a panel of ears that we use to validate the reference curve. Okay, so we'll validate the reference of the speaker, like the 25 that is here. So this is the reference, and then it has to be kept within 1.5 dB of this reference, and to match as much as possible the reference. But this is the reference that's been validated. So we check frequency response, we check for every single product that's produced, harmonic distortion, that has to be 40 dB and below the signal, non-harmonic distortion, that is all the background noise, and if you have a little, this is if your speaker's not airtight, you'll hear little market, so non-harmonic distortion, and also phase response that has to be flat from 150 hertz upwards. And every single speaker receives this, and then we plot the frequency response that we deliver with every single speaker. When you buy a precision instrument, it comes with its calibration curve. then you know it's calibrated and it can do its job. So that's what we do. And we keep these and we check them when we have speakers that come back 15 or 20 years later. We check them and it doesn't move much. Storage of raw material, finished product, and the shipping that's used today. The idea with sound is pressure going up and down. But associated to pressure going up and down, you also have this movement of molecules going back and forth. It was called sort of acoustic velocity. So now imagine you're swimming in the sea and you have waves. That's the pressure going up and down. But you also go back and forth. That's the molecules going back and forth. Now, if this water that's going back and forth hits a rigid wall, it has nowhere to go than to go up, building pressure, and that will create an echo, and the wave will come back. So that's the mechanism of the echo. Now you can imagine that if you move this wall back and forth in phase with this velocity, you can absorb completely the waves so that there's no wave crashing against the wall and coming back. So this is what this is based on. Now imagine, instead of moving a wall is quite difficult in acoustics at these frequencies. So what we do is we move what we know how to move very accurately as a driver. So you move a smaller area, but you displace over this smaller area the same volume of water or air, if it's acoustics. So this is what we're doing. So you can imagine absorbing this wave out of a small surface. You have to move a lot faster. You have to go faster. So you're increasing the velocity for the same pressure. So you're reducing the impedance. And this is exactly what we do here, is we impose a very low acoustic impedance of 100 pascals per meter per second. So how it works is you measure the height of the wave. That's in acoustics, well, it's a pressure sensor, that's a microphone. And it says for this height of the wave, to avoid any echo, I have to move back so much volume of water, of air in this case. So that's the driver that's behind here. And you have about 4 or 5 centimeters to be accurate in time, in phase.
Inside there's a driver as well.
So inside there's a driver, yeah. And that has to move. So this is how it works. And then this grill here that's got small perforations, the idea is that it transforms part of the pressure into velocity, and then you can absorb it behind. The analogy I always talk about is a bucket full of water. You have a bucket that's full of water, there's pressure at the bottom with no velocity. And if you punch holes in it, small holes, the water will come out with speed, but no more pressure. So there's more velocity than pressure behind this. And it has to be extremely accurate in frequency and phase, of course, with minimum latency. And that's why analog technology works better. So we developed it with the University of Lausanne, the EPFL, and the HEPIA in Geneva, University of Geneva. Now these have to be calibrated. So how do you calibrate it? Its role, what it does, is impose an acoustic impedance of 100. So you have to measure that. Okay. So the acoustic impedance, you have to measure these movements of air that change direction 50 times per second at 50 hertz. Very difficult to do in low frequency. So especially on the surface, you can do it over a bigger distance. So we had to develop a device to measure this velocity, which we can show you here. And yes, it's very close to being a ribbon microphone that we use. Yes. So we measure the pressure with this normal Omni microphone, and then this is a microphone, ribbon microphone that is sensitive to the movements of air, so the velocity. But then you have to calibrate this microphone also. So here what we use, I'll just cover it up. So to calibrate the microphone, we developed another very complicated, like this, where here basically 2 drivers that will move in opposite direction, like this. And inside, well, you know the speed of the air that you have here. And we can put an accelerometer here, you can close it up, and basically you put your microphone in here and you can calibrate it. What I'm trying to say is that when you develop a new technology like the AVAA, you have to develop the measurement instrument, and you have to develop the way of calibrating the measurement instrument so that you make sure that what you do is accurate. Calibrate the calibrate. And then this AVAA, this imposed impedance, if you put it in one room or another, or in one corner or another, it'll have a different effect. Because typically in these room mode frequencies, the map or the of pressures is different. So you can have high pressures in some areas and the others.
What do you advise? Do you need to just check out the best place, or is there a rule?
No, so the basic rule to position them is, first of all, you look in your, well, first of all you position your listening position and speak as the best possible, okay? Then you sit in your listening position and you have to identify which are the disturbing room modes in your listening position. That's the first thing that you can do quite easily with different, you can measure them or you can hear, you can just listen. And then, so for example, you'd have 40, 60 and 80 that are a problem. So then what you do is you play, then the second step is you have to determine where it comes from. So you'd play a 40 hertz sine wave and you can walk around the room and you can quite easily identify where the high pressure zones are at 40. And then you do the same at 60, the same at 80, and you can see which are the corners that will benefit most from the AVAA. But it works, then there's also a low pass below about 200 hertz or something like that. So they're efficient up to 150, then the efficiency goes down and they really only work in that range. Bobcat.
De hemel en de aarde, de wijdheid van het land.